So again, I just drew a nice bold-faced line where the zeros are to try and exaggerate that's 0 meters per second. And from here, what we're asking you to do is I think pretty easy. I want you to create a position versus time graph. Be intentional. So make sure your position versus time graph has all the qualities we talked about last week when we did this. So I want to walk around in the first 5 minutes or so and see that you got number 1 done. Over here. So let's talk about the first one and what my expectations would be. And there are several things here that may seem subtle, but if you're hoping to get a perfect on your first pop quiz, you might want to make sure you have these written down. The first thing I want to say is, do you notice that this graph has kind of got 3 sections to it? So when I see this graph and I'm trying to make a determination as to what's going on here, the fact that there are 3 sections is important. Not all graphs are going to have sections, but many do. And they're not always as obvious as this one. But this one's pretty obvious because I see abrupt changes in the object's velocity. I'm looking at time equals 0 and noticing that we are observing the object over the span of 10 seconds, which means your position graph will also be an observation of the object over a series of 10 seconds. So the first thing you could do just to get started is to identify that the horizontal axis, 2, 4, 6, 8, 10, is going to be 10 seconds. I'm going to point out that even here, I do make mistakes. I want to try and use up as much of the graph as possible. Often a point is issued on the AP exam for using more than 50% of the provided space. If you didn't use 50% of the provided space, you wouldn't earn that point. So I would encourage you to use the space provided. You'll notice I'm labeling it because you will always be given points for correct labeling of an axis. And I'm putting position here. That statement, that tells me where the first dot's going to be placed. It says that at time equals 0, the object is at the origin. So at time equals 0, the object is at the origin. So all of you who started your dot somewhere else, they're all wrong. And that's a pretty big group. All right. This is a velocity graph. Its area tells me the displacement. Area is the portion of the graph bounded by the curve and the axis. We reasoned our way through it as well. So some of you could reason your way through, and that's fine. But I would encourage you to get away from just reasoning here. There's going to be cases coming up where reasoning won't work. But you could reason this one. The object traveled 2 meters per second for 4 seconds. Well, if it's traveling 2 meters each second, and it does that 4 seconds in a row, it's going to move 8 meters. Now, that part's pretty easy, but that's something you can do because the velocity is staying the same the whole time. When the velocity is no longer staying the same, that's going to be a difficult argument to make, which is why I need you to transition to having a more robust understanding. But can't force you. All I can do is tell you that I'm doing the same thing by finding this area. You remember doing this last week? Hope so. All right, so that means this section had a displacement of positive 8 meters. Like I said, I'm going to go as far as to even put the positive there, because this is velocity. Velocity has direction. And so I'm making sure in my head I know the direction is positive. It's moving in a positive direction. There's another section here, though, so I'm going to take a look at the other section. That's here. It has a width of 4 seconds as well, but it has a length of -1 meter per second. So in trying to figure out the displacement over this interval, -1 times 4 is going to be -4 meters. So it seems to me that I have 3 sections. Now, I only talked about 2 sections. I didn't talk about this section. Why didn't I talk about this section? What's that? You're fine. Go ahead.
0.
What's at 0? the velocity is 0, which means it's not moving. Or the first 2 seconds, it just stays there. It has no velocity. So this ultimately is 0 displacement. All right, displacement is change in position. My object traveled 8 meters forwards and 4 meters backwards. I need to identify an appropriate number line in the vertical direction that can accommodate the motion of this object. Since it goes 8 meters forwards and then 4 meters backwards, it never gets further away than 8 meters from the starting line. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 meters along my number line here. I've accommodated the motion of the object. All right, in the first 2 seconds, the object doesn't move. That means that my next dot's going to be there. In the next 4 seconds, it moves forwards 8 meters. So I know that at 6 seconds, it's 8 meters away from the origin. So I'm going to put a dot right here. Try to line it up with the 8 meter mark and line it up with the 6 meter mark. Now, I have to connect those 2 dots together. This is not done in an arbitrary manner. It has to be done intentionally, which is why I suggested you take a meter stick out, or I'm sorry, a meter stick might be a little big, a ruler, straight edge, driver's license apparently works. I even saw credit cards last class period, but you won't be able to take those out in the AP exam. Get yourself a small ruler and intentionally draw a straight line between those two. The reason I say the word intentional is because they are looking to see if you understand that the velocity was a constant. If you hand draw that in, they might interpret that as being curved. You need to be intentional. From here, it moves backwards 4 meters. So that's going to take it from 8 to 4. So 7, 6, 5, 4. This is right there. Something like that. And again, that was done in a constant way. So I will try and be intentional about it as well. This is what the graph should have looked like. Now, I had about 60% of you who were really close to this. Look great. But I'll point out all the things I am looking for. Clear articulation of where the points are of its motion. So, these data points, that needs to be clear. An appropriate use of the axes, using as much of the graph as possible. Labels on the axes that indicate the units from your measurement. A reflection of the starting line being where you're told to place it, and an understanding that you can't get that from the velocity graph. And then intentional use of straight lines to indicate constant slopes. Those are things I will be grading. So, based on my cursory walk around the room, like I said, 40% of you couldn't do this, with some of you not getting anything down on the paper before I actually came by the second time. So I think that this should be enough. If this is not enough for you, I will post practice tonight, so you should practice. But you should demonstrate that that was enough, and now you have this one completed. So I'll give you another minute or two. I want you to complete this one. I really want to do this one. But I think I'll need to probably make sure that I've captured those 40% of you who haven't acclimated yet. Although this was stated, it gets more and more confusing as your graphs get more complicated. Area is between the curve and wherever 0 is. So when you're looking here to figure out how to deal with area should stop at 0. That's why I drew that big bold line in and recommended you did the same, because a lot of people will carry this down to here, or worse, will carry it all the way down to where the bottom of the graph is, and that's not okay. So that's an area, that's an area, that's an area, those are areas. It's bounded between the curve and 0. Perhaps I can go through this a little bit more quickly. Let me start with, I see 3 different areas. Do you see 3 different areas? So area number 1, area number 2, and area number 3. And length times width, 5 times 4, positive 20 meters here. Questions about that? All right. Negative 1 times 5 tells me negative 5 meters here. Everybody okay with that? And then it looks like negative 3 times 1, negative 3 meters here. How's that? Any questions about where I got any of those? So I went forwards 20 meters, backwards 5 meters, and then backwards 3 meters. So it looks like I started at 0, and I'm ending at 12 meters. All right, so let's see what that looks like over here. First reminder is that we can't get the starting position from the velocity graph. We have to be told the starting position from something else. And again, we were told at the very beginning to start at the origin, so my first dot's at the origin. In the first 4 seconds, I moved 20 meters. So I've already got my 20 meters here. That puts a dot there. The velocity was a flat line, which means the velocity was constant. So I need my slope here to be intentionally constant. Now, over the next 5 seconds, the object slowly goes back 1 meter. Slowly goes back 5 meters. So I'm at 20, 18, 16, 15. So 15 is like right here. So something like that. Now, in the next 1 second, I jump back 3 meters. So I'm at 15, I want to drop to 12. So let's see, 2, 4, 6, 8, 10, 12, something like that. And again, intentional. My graph should look something like this. On graph paper, I'd expect it to probably be a little bit more exact, but notebook paper like this, you should be as close as you can make it. Reasonable. Questions? Yes, sir?
So do we only need the max number on the vertical axis?
You need enough to accommodate the motion of the object. So max is probably the right word there, but I don't want to say it that way because you can have any number of other changes. We haven't really seen one that does that. Now, I think that this is kind of basic. This isn't the level at which I'd like us to be working. The level I'd like us to be working are these down here. Hold on. The level I'd like to be working is these like this. I want to work one like this. There's something different here, and I hope you know what is different here. Now, how we deal with this, that's going to be a whole nother thing, but there's something very different here. This object does not have a constant velocity. This object's velocity is constantly changing. It starts from rest, and by the end of our interval of 10 seconds, it's traveling 20 meters per second. So I know just by looking at this graph that my position graph is going to be starkly different. The position graphs we've had before have always assumed that the object had a constant velocity, and this is an indication that the velocity is constantly changing. But all the rules, the velocity graph doesn't tell me where I start. The start of the problem told me to use the origin as my position. That's still true. Next, the area under the curve is what's going to give me the displacement, the change in position. I'm still going to do that here. I'll point out that 0 is right there. So if I want to intentionally indicate that this is the 0 axis, I can. But my area will now be here. Well, luckily, I've had a course in geometry, and I'm pretty sure you guys remember how to calculate the area of a triangle. So 1/2 base times height work for you guys? So I'm going to do the same thing, 1/2 the base is 10 seconds, and the height is 20 meters per second. I'm still doing just area, nothing fancy. But I will point out that this gives me a displacement of 100 meters. And it's positive. So there's only one section to my graph. So I've got the section now. I'm going to go over to the other side here and begin my position versus time graph. And you're going to be frustrated perhaps with me, but I'm short on time. But I don't have to worry about other middle sections or any middle pieces. I know where it starts and I know where it ends, and that's it. So and now I have to connect these. And herein lies the difficulty. When I go to connect these two dots, I have to remember that the velocity starts at 0 and ends at 20. So that means, and I'll translate it for you, the slope starts at 0 and ends at a big positive number. So the slope here must be flat because that's a 0 slope. And the slope here must be steep because it's got a slope of 20. Yes, sir?
So would that be exponential?
I don't think it's exponential, but you guys use that phrase to indicate a curved graph. There are lots of graphs that curve upwards. So I'm not trying to say what kind of function this is. I am saying that the velocity does change in a regular and repeated way. Hold on. Right, I notice that the velocity is getting bigger in a regular way. Wouldn't you guys say that? With every second, it adds the same amount of velocity every time. So I want to connect these two dots in such a way for the slope to be low in the beginning and high at the end. Maybe something like that. Some way of connecting it so that it has a shallow slope at the beginning and a steep slope at the top or at the end. Now, you said exponential, and while you guys pack up, let me just point out, exponential means this. But all of these graphs would look like this. Right, they would all slope upwards. So I don't know which one of those it is. Not yet. We'll have to figure that part out. Perhaps we could start here and maybe talk about a few of the things that we discussed the other day. Some points that might be of use in looking at what you are supposed to do with the information presented. Now, let me be really clear. There's a variety of things I can list here. I'm only going to list the stuff that we already talked about. So, for example, a position versus time graph. We talked about that in this, with some reflection on the two cyclist problem. We had cyclist A and cyclist B. And in discussing that question, we came up with a couple of straightforward pieces of information. First, position graphs tell you where the object is. I know that sounds silly, but trust me when I say you need to be able to tell me what the use of a position graph is. So it tells you where the object is. You may be able to get other pieces away from it, but that's what a position graph does. It tells you where the object is. You told me, I didn't tell you, but you told me that the slope I helped you with the vocabulary, but you were able to come to the conclusion that the slope of this graph was how fast the object was traveling. I put a vocabulary word to it because it not only told us how fast the object was traveling, but depending on whether the slope was positive or negative, also indicated in what direction the object was traveling. So that's why the word velocity is used here. And that's it. That's the extent of what we came up with. There are other things we can get from a position graph, but that's the extent of what we discussed the other day. We also discussed a velocity versus time graph, and I think, again, what does it tell us? Well, first, it tells us how fast and in what direction the object was traveling. That's what it tells us. How fast and in what direction the object was traveling. I'm really careful about this next part because it does not tell us where the object is. It doesn't contain that information. It does not tell us where the object is. It can't give us any positions. But we did determine something about the graph that we could use. It can tell us the change in the object's position. So it can't tell us where the object is, but it can tell us how far the object moved. So, and that's the area. Bless you. The word that we use here is displacement, which is the word I used in class. The area can tell us the displacement of the object. Displacement is defined as change in position. There are students in this room who don't understand what I'm about to say, and that's okay. Write it down anyways. You're going to need to come to understand it. Knowing an object's change in position does not tell you its position. So you need to be aware of that. That's different. We need a point of reference if we want to know the object's location. And it was given to you. It's at the top of the worksheet. It tells you to begin the object at the origin. So it's telling you where the starting position is. But the graph can't tell you that. Now there's more information to put in this chart. This is just to get us started, but this is all you need to do what that we have here all still apply. None of these rules are different. For example, on a position versus time graph, the slope is the velocity.